So in one of the last videos, we built a digital level that has a rotating screen and uses a 6-axis gyroscope to function as any spirit level would. But some folks have asked for a rundown of how the actual code works, so here it is. You'll need these 4 libraries installed. So in the source code that's posted up on GitHub, you'll also need to grab Jeff Roberg's MPU 6050 library, and here's the link for it. There's a lot of libraries for the MPU 6050. I'm using Jeff Roberg specifically, and there's some differences between all the libraries out there. So if you try a different MPU 6050 library, it may not function correctly with this particular application. So make sure you grab Jeff's. And then we'll need the Adafruit SSD 1306 OLED library for the graphics display. Adafruit also has a supporting graphics library for it, and I'm using one of the Adafruit font files for the actual text that goes on the display. So you want to make sure you have these 4 libraries installed in your Arduino IDE before you compile this code. And then we'll include those libraries here along with the kind of standard EEPROM library, I2C dev, and wire. This MPU 6050 6-axis motion apps is the inclusion for using the DMP functionality of the gyroscope. And this offsets some of the processing to the MPU instead of having to do all of the calculations on the Arduino Nano side. And it does that by loading a special firmware to the MPU 6050. And that firmware is housed in this header file. Now there's different versions of motion apps. Jeff includes, I think, the newest version in there as well. But I'm specifically using the 2.0 version because it's a little bit smaller. And I was running out of program memory space on the Arduino Nano, more so to do with the text that's needed to display on the screen. So I suggest sticking with the 2.0 version. The Nano will have to hold all of the firmware to load to that DMP chip. So using the newest version takes up more programming memory space because that firmware is a little bit bigger. So we'll just declare some general variables for our use here. We're setting up what our screen size is and initiating the display. Defining what our buttons, what pins they're connected to. The menu timers are for when you scroll through the menu using the buttons. If you don't press anything for a certain amount of time, it will automatically exit the menu screen and go back to just displaying the angles that you're at. So this menu timeout sets that. Right now it's set to 10 seconds, but if you change this to 5,000, you'll have a 5-second timeout. So 10 seconds may be a little bit long, but you could play around with that. And then the mode that we're in, if you remember on the menu, you have normal mode, which rounds all the angles up to the nearest whole number. Precision mode will show you 1 decimal place, and this is just a variable holding for that. Then we're setting up the I2C address for the MPU gyroscope. And in my case, it's 68 hex. If yours is different, you'll want to change that value here so that your MPU will initialize correctly. And then just some variables that are needed for the MPU following some of Jeff's examples. We'll jump down here to actual setup. Initializing I2C. The serial begin is really for debugging. Once everything's together and it's in its case, we're no longer using serial anymore. We're not hooked up to a physical computer. So you can really comment this line out. It's not necessary. We'll set our 2 menu buttons as inputs with pull-up resistors because the menu buttons are tied to the pins, and then the other side directly to ground. So when no one's pressing a button, it is in an active high state. A low would mean somebody actually hit the button. It ties that pin to ground and pulls it down low. Initialize the display, clear everything, kind of set up what our text color is going to be. It's a black and white display, so white. And then just give us a little startup message so we know something's at least going through the setup loop and things are looking okay. Then we initialize the MPU 6050 itself, and we grab calibration. Now, this is getting the stored calibration, which calls this routine here, and it's just going to read out of the onboard EEPROM of the Arduino Nano the bytes that we saved from the last time we calibrated. And just built a couple of little routines to kind of help those along. Because it's a 16-bit value, we have to do some bit shifting to save and pull things correctly. So that's what these two routines are doing, to both write to the EEPROM and read from the EEPROM in a little bit easier way. So once we have our calibration, now the calibration, first time using it, is going to be all FF in all of those spots in the EEPROM. So it's going to be way off. And the very first time you build this and set it up, you will have to calibrate the device. Afterwards, I haven't had any issues. It seems to stick. I think if you change like huge temperature differences or your elevation changes dramatically, you may have to recalibrate, but I haven't had any issues working around the house sort of stuff. So it seems to, its accuracy kind of stays where it's been. So that's been pretty cool. So we make sure that initialization went correctly. Part of that initialization for the MPU is loading that firmware for the DMP processing. So as long as that worked, we have no problems. If it didn't, we'll display on the screen that the IMU failed. And then it's a little tricky. There's probably a wiring issue with the MPU 6050. Maybe it's a bad board. If you bought the ones that I bought, they're really, really cheap. So sometimes you get a board that's a little iffy. But if everything went well, we just jump right into the main loop. So in the main loop, we're checking first to see if anybody hit the menu button. If not, then we check to see that the DMP is actually functional on the MPU 6050. If everything's good there, we just keep looping. And then we get the actual values for the angles. So it's pulling those angles in quaternion form. And for our purposes, we want to convert those back to Euler to be able to decipher kind of where we sit in the real world space. Now, this may be a little bit backwards, but this has worked really well for me. When I started with the DMP pulling Euler angles from the get-go, there was a lot of drift and things were way off. But I found that pulling them in quaternion form and then processing them back to Euler as needed was giving me much more stable results. So that's what we're doing here. This will take those values from the MPU 6050 in quaternion format and send it to this routine, which was pulled right out of one of Adafruit's examples for a BN0555, another type of IMU. I think that one might be a 9-axis, but they have all the math here to convert those back into quaternion form, and I added into this routine to convert the radians to degrees so that my mind can function a little bit better. degrees make more sense to me. So once we have that, we'll have our X, Y, and Z axes, angles in degree format. And from there, it's where things got a little bit messy. From there, it was just kind of trial and error to figure out if the level is sitting down in a position that it's going to check a level surface, which way is Z normally pointing, which way is X pointing. And it's just a bunch of if statements to say if the X angle is less than 0, but at the same time the Y is between, is less than 35, is greater than 35, but less than 90, then we're facing this way. If it's the opposite, we're facing a different way. And so that's what all of these routines are doing here. You also notice I put a lot of comments in my code, so please read the comments. They'll probably do a lot more justice than I'm doing here. And for each of these, we're cleaning up what angle we're at, because the MPU will want to tell you kind of 0 to 180, maybe to 360. We're doing just a little bit of basic math to make sure that we're always within 0 to 90 for each kind of quadrant that we spin in. The disp rotate is telling us also what format do we want the screen to be in. The level in its normal state, you want the text to be readable to you, and as you rotate the level itself and your angles are changing to check if you're vertical or plumb or upside down, which is still measuring a level surface, just the device itself is upside down, we want that screen to keep rotating with it. And so that's what we're doing here. Depending on what our angle is at, we'll change the actual screen orientation to print the text upside down or right side up or in a vertical position from top to bottom. And we use that to function that to make the display work. And then finally, we actually show the data on the screen. So format display will bounce into that subroutine. We'll bounce into the format display subroutine where it takes the angle value, a integer value of how we want that screen to actually display rotation wise, clears the screen. If we're in precision mode, then we want to not round the number. We want to display 1 decimal point. We set up where our cursor should be on the screen, so where we want to start writing text. Our font sizes, because when the screen rotates, when it's in a vertical position, the font has to be a little bit smaller to fit on the screen correctly, versus in a horizontal position, you have a lot more room to work with. And finally, print that angle on the screen itself. Then we go back, still within the format display. We then check to see, is this angle plumb or level within plus or minus 1 degree? So we'll add a little block of text that says either plumb or level, again depending on the rotation, to the display under where the angle is shown. Now, if you want to make it plus or minus 2 degrees, 0, you can change that value right here. So we take whatever the absolute value of the angle is, round it to the nearest whole number. If it's 1 or less, we consider that level. So if you want to make this super accurate, you could change this to 0.5 or 0 if you want to be super precise. But you may never get that level sign. I mean, this is still a 3D printed enclosure, and depending on how you position things in there, if it's a little bit off, it's going to be real hard to get super precise with a kind of homemade device like this. So I kept it at 1, and this is plus or minus 1 degree. The kind of plus or minus side is handled by the absolute value. So whether it's a negative angle, meaning you're tilting one way, versus the positive angle, you're a little bit off by the opposite end, the absolute value is just telling us we don't really care how it is, just is it 1 or -1 in the real world, and we'll call that level. And then we display that with a kind of white background and black text. So this is the brains of it right there. That's everything that handles what angle are we at, how the screen rotate works is fairly straightforward. The bunch of if statements to figure out what orientation we're sitting at is messy. There's definitely a better way to do this. The math gets really complicated with the MPUs, so it's the best I could come up with after hours of tinkering with things. Let me know if you have any better ideas or you know a better way to do this. I would really be interested in that. Leave a comment down below. So going back into the main loop, we'll start looking at when the buttons are pressed. So if somebody does hit the menu button, because this executes super fast, hitting the menu button at any point will be fine and trigger this. The user won't notice any delays. If the menu button is hit, we'll bounce into the menu main wait routine, where we actually display the menu. So the display menu routine does exactly what it says. We'll display the actual menu items on the OLED display. In our case, we have normal, precision, and calibrate. And depending on which item is selected, that's passed into this routine, a white box will be drawn around that item so the user knows which menu item they're currently about to select. So then we go back into the menu main wait routine. We've now shown the menu on the screen and we kick off the timer. So we capture what the current Arduino Nano timestamp is with millis, and we start to then loop through this piece here. If we haven't yet approached the timeout period, then the display will sit there on the screen, or the user is pressing buttons which will constantly reset that timeout. So if I enter the menu and do nothing for 10 seconds, it will exit and bounce you back to the main display. But if I hit any button, either the menu button again to scroll through or the enter button to actually perform an action, it resets that original counter so that the clock basically starts again. So now we wait and see, does the user hit the menu button again? If they do, then reset that counter, increase the menu item number because now they're basically selecting and moving to the next menu option, and update the display with the new menu item we want. However, if the user selects the enter button, then whatever menu item we are on, we want to kind of enter that mode or that menu. So menu item 0 is precision mode. Is normal mode. Another typo. Menu item 1 is precision mode. Menu item 2 is special because that brings you into the calibration menu. So while these will just set precision mode true or false, which again in the display routines for the angles, we'll just choose whether or not we round to the nearest whole number or show 1 decimal place. Selecting calibrate will bounce into this calibrate routine. So in menu calibrate wait, this is again kind of the same logic as the main menu, where we display the calibration menu items and we start a timer to wait and see if we time out. Because the calibration menu has 2 options you can choose, we again want the user to be able to exit that without having to press anything, just for convenience. So in the display calibrate routine, again, we have an item select that we pass there. We set up to display the text lay me down face up. and then a start and an X for exit. And we'll draw rectangles again across the currently selected menu option, which is either going to be start or the X. And again, just like the main menu, if the user keeps hitting the menu key, which acts as a select key, it will reset the timer and redisplay with the box around the selected item moving from either start to X, back and forth, back and forth. But if they hit the enter button on one of those items, we see which item is currently selected. If it's start, we will bounce to start the actual calibration. If it's the X, then we're just going to exit all of the menus altogether. Now for calibration, we'll display on the screen calibrating and then call this routine set calibration. Once this completes, we'll show the user a complete screen so that they know it's done. But in set calibration routine, we will use the auto calibrate feature of the DMP within the MPU 6050. So we're going to say we want to run this 6 times for the accelerometer, 6 times for the gyroscope, and it essentially kind of averages out those results. And we pull those results by reading the register in the MPU 6050 through I2C, pull that data in, and we're going to take that data and now we're going to save it into EEPROM so that we can pull it back in the future each time the device is turned on. Now the calibration values are 16-bit, so it's 2 bytes, and we use, again, that EEPROM write word routine to take the 16-bit integer, we break it into 2 bytes, and save that into EEPROM. So even though we have an X, Y, and Z calibration value, same thing for the gyroscope, X, Y, and Z, we're using 2 slots in EEPROM for each of those values. So this will actually be broken into 2 bytes, 2 bytes, and 2 bytes. Now on get calibration, we're actually reading back the last saved values from the onboard EEPROM of the Arduino Nano. And for each read, we actually want 2 bytes back because the calibration data is a 16-bit integer. However, the Arduino EEPROM read and write is working with a 8-bit byte. So I have these 2 little routines here that will provide us with the 16-bit data that we want passed back. And all we do is read 2 address values, put them together using some bit shifting, and return those results. And the opposite for actually saving it. To write a word, we're taking the address we want to start writing at, the value, and we'll take that value, it's assumed to be a 16-bit value, break it into 2 pieces by bit shifting, and save those into the EEPROM. So get calibration is using the built-in routines in Jeff Robert's library to actually just pass those values into the MPU. This needs to be done with each startup. The MPU 6050 does not save these values within itself. So every time the device is powered off and back on, the calibration values have to be reloaded. Otherwise, it will use its defaults and they could be all over the map. So that's the long and short of it. I encourage everybody to read the comments that are written in the source code here. If you have any questions, please comment down below and I'll do my best to answer all of them. It's really not super complicated, even though it looks like a lot. It's pretty straightforward. The bulk of it is really that block of if statements in the main loop. And that's it for today's video. So thanks for watching. Thanks to those of you who have subscribed. If you haven't yet subscribed, please consider subscribing and throwing a thumbs up on these videos. Trying to build this channel up. Could use all the support I can get. Appreciate it. We'll see you next time.